right, so we're here today to talk about semiconductors in the age of software-defined vehicles. And we're going to touch on a range of topics ranging from industry challenges to chip safety and opportunities in ADAS and AI. We're glad to be joined today by Bob Swan and Les Kohn. So quick introductions. Bob has had a distinguished career, most recently as the CEO and CFO of Intel, overseeing 110,000 employees, $78 billion in sales, and increasing annual sales by over $20 billion during his tenure, as well as overseeing the acquisition of Mobileye. He was previously the longtime CFO of eBay and was an executive for many years at Electronic Data Systems, TRW, Webvan, and GE, among others. Today, Bob is an operating partner at Andreessen Horowitz and also sits on the boards of Nike, Flexport, GoTo, Kearney, and the American Heart Association. Welcome, Bob. And Les, for the past 19 years, has been the co-founder and CTO of Ambarella. Les is well regarded in Silicon Valley as one of the leading chip architects in the industry. Ambarella focuses on low-power, high-performance SoCs with an emphasis on video, radar, and AI processing. Ambarella has invested heavily in ADAS and AI, and now has one of the most compelling automotive compute offerings in the market. Prior to Ambarella, Les was the CTO at Afara and a chief architect for a number of notable products at Sun Microsystems, C-Cube, and Intel. Welcome, Les. All right. I think a topic that's on everybody's minds with regards to the semiconductor industry is the chip shortage, which has been a big topic since 2021. So Bob, what caused the shortages and how has this affected strategies in the industry?
Boy, I thought in my new role I got away from that question a long time ago, but I guess not. Hopefully this will be the last time. I mean, in so many ways, the chip shortage was almost like one of those perfect storms. But at the same time, perfect storms seem to be coming more and more often. So I think the need to learn from it a little bit, even though circumstances may be different, is extremely important. But from my vantage point, there are really kind of four things that happened. One, unexpected and explosive demand. That has a tendency to constrain supply chains. And on top of that, supply chains that really got disrupted by COVID in many ways. And then third, as chips have become more and more relevant in more and more things, the sophistication and maturity of demand forecasting hasn't quite kept up with the relative importance of chips in a variety of different industries. And last, I think more from the semi industry, given that more and more industries are dependent on chips, having robust, faster response time for incremental demand is really important. So if I just touch briefly, explosive demand, chip demand primarily for PCs over the course of 10 years from 2010 to 2020 essentially declined each year, almost, with maybe one exception. So demand was coming down, and I think as we all sat in our conference rooms at the second half of 2019, the prospects were for high likelihood of recession in the second half of 2020. So declining volume and then high likelihood of recession. And historically, PC demand tightly correlates with GDP. So the industry was expecting significant declines in PC demand in the second half. And then obviously with COVID, everybody needed a couple computers. So instead of double-digit demand in the second half of 20, demand actually increased in the high teens or in the mid-teens for the year, but really back half loaded. So it put this enormous demand for not just PCs, but clouds. We were more dependent on Zoom, which are very dependent on clouds. So all the cloud service providers needed compute as well. So demand came significant and unexpected. And then the coordination required, we never figured out how to make chips or assemble chips from home. So in the midst of COVID, how do you rally both with governments and with employees a safe environment where you could get governments okay to get your people back to work was very important. Just the third, and this is particularly, I think, relevant for the auto industry, the supply chain with OEMs for electronics in the PC industry in particular is relatively mature. So the industries have been working together quite a bit for a very long time, but for auto, not as much. And the transparency and the effective communication that will be required going forward as more and more chips go into a car becomes extremely important, and much tighter coordination, much closer transparency, and much longer profile of what demand cycles look like, giving it's not just about number of vehicles manufactured, but how many chips are going to go into those vehicles becomes more important. So a perfect storm created quite a nightmare for so many people, but the reality is I think perfect storms are going to happen more and more often, unfortunately, and therefore the learnings that we have coming out of this one I think are going to be extremely relevant going forward.
So when we talk about chips in vehicles, a hot topic right now is, of course, more companies getting into chip development and chiplets being a really interesting field with regards to IP in chips. So Les, what are chiplets, and what's your view on how chiplets will impact technology development in the semiconductor industry?
Yeah, so chiplets are an advanced packaging technology that allows you to combine multiple silicon die and connect them with a high-density interposer, which itself is another silicon chip, essentially, and put all those things into the same package. And this technology was developed originally for high-end CPUs and GPUs. It's the kind of thing that you see used in these $10,000, $20,000 GPU chips, and similarly for CPUs. More recently, people have proposed using a standardized interconnect between these chiplets called UCIe, which in theory will allow you to mix and match chips from different vendors and build a kind of customized system without having to design chips from scratch. But unfortunately, there are some significant challenges with this technology. Because it was developed for essentially cost-no-object chips, the costs are quite high. This interposer layer, which has to be a very large die, is expensive. The manufacturing capacity is currently quite limited. And so it's not clear how cost-effective it can be for high-volume automotive applications where cost is a very important factor. In addition, making it reliable enough to meet auto-qual requirements is another big challenge that has to be worked out.
And of course, chiplets are not just about the technology, but it's also a business discussion with regards to intellectual property. And so, Bob, from a business perspective, how do you think that auto companies and semiconductor companies should think about the build versus buy regarding the IP in their chips?
Yeah, well, I'll maybe do the semi because I'm not nearly smart enough to give the auto response to that. But I think in semi, I mean, obviously, IP is so important in everything you do. So for every piece of IP, the discussion around do we make / build, do we partner, do we buy is incredibly important. And I think there's probably three macro characteristics and then one that links back to packaging technologies. But one, to state the obvious, what's the strategic relevance of that IP and the solution you're trying to solve for your customer? And the higher it's strategically relevant, the more important is, build, in my mind. The second important component is, do you have the capabilities? So you may conclude it's really important, therefore we must build. But if you don't have the relative competencies to do it, then all else equal, a bias towards partner or purchase. So those are kind of the two really important ones. And there's a third element called time, pace. What's the importance of pace? Is the industry going to change? If we want to build, but it will take long, is the industry going to move so fast that we're going to miss it along the way? So strategic importance, relative capabilities, and pace are probably the three things. And then the answer you get today may be different than the answer you get tomorrow to the exact same question. And in some ways, advanced packaging, over time, my belief, and Les knows much more about this than I do, but my belief in advanced packaging is, the relevance of the packaging technology begins to become more important in solving the problem for your customer than the individual slices of IP that goes into that package. So I think differentiated technologies that come around over time may change the answers to those three fundamental questions about strategy, capabilities, and pace, making the right decision.
So relevant to the build-buy convo, Bob, you oversaw the acquisition of Mobileye at Intel. Of course, why did Intel do that acquisition, and what was it about the Mobileye tech and business that was so attractive?
So we acquired Mobileye in 2017 for roughly $15 billion, and it had $400 million in revenue at the time. So it was a pretty steep price to pay, but it was a fairly easy decision. And I say that because as we were thinking about the industry and the evolution of the industry, in a 5G and AI-enabled world, a very strong belief that compute-intensive stuff was going to move from the PC to the cloud, to the network, and to the edge. Very strong belief. And then in the edge, where are the biggest applications, and a bias at our end, how do we make sure that we have the ingredients inside the biggest applications? So for us, the biggest industry was automotive, and the biggest application was ADAS and autonomous driving. And therefore, going back to the build versus buy versus partner, we felt like we needed to own the IP to develop a much bigger presence in a movement of compute moving to the edge in an industry relatively big with advanced technology that we thought was going to be increasingly important.
And then, of course, after your tenure, they did the spinout. And what do you think of that?
I think it was brilliant, honestly. And I say that because it's, wind the clock forward, Mobileye, if it was $400 million revenue at the time, I think it's going to be $2 billion this year. So it's, it's a 5x since 2016 timeframe, because it got adopted on more and more platforms, i.e. if we were to build it our own, even if we could, we would have lost out by the time we had a product. But it's 5x in size, but at the same time, it's less than 3% of the revenue of Intel. So it's very hard to get credit through the eyes of investors for a high growth business inside a slower growth business. So in that case, you have to entertain ideas to how do you monetize and effectively get credit for IP that's inside a large company. So the decision to monetize, I just think made a lot of sense because they were able to maintain control. So, they said they're going to keep 80%, and I think they're north of 90% equity interest in the company, so they retain control. However, they've illuminated a very valuable asset for the market by letting the market speak rather than them tell people how wonderful it is. And they raised a bunch of capital. And as they've thought about getting bigger and bigger in the foundry world, that's an incredibly capital-intensive move, and therefore access to capital through monetization of a very important asset, it makes a lot of sense. So I think they've retained control, and they monetized an asset and illuminated it in ways that they just couldn't do it as a wholly owned entity.
So Les, Ambarella acquired VisLab, which is, of course, less known than Mobileye, but still very, very important, in 2015. And VisLab has pioneered a number of advances in computer vision and autonomy technologies. So how has the VisLab acquisition impacted your strategy and technology?
Yeah, so we've always believed that in order to design an efficient chip, you need to have a deep understanding of the algorithms that are going to be running on that chip. And so VisLab was very critical to us to be able to understand the kind of processing that you need to run a full AD stack, not just perception, but fusion, planning, and how they all fit together. And over the years, we've been trying to aim at a goal of taking their stack, which originally was running on a trunk full of PCs, and bring it down to something that can run on a single chip. And as of last year, we finally had the chip that can do that, and we have been working on a new version of the stack, which is AI-based across all levels, and trying to really optimize the implementation to be as efficient as possible, but also to be able to handle a wide operation domain, including dense urban driving.
So related to that, let's talk about AI processing. So naively, AI processing is just a bunch of matrix multiplication. And of course, GPUs, they've been doing matrix multiplication for decades. So it seems simple, but of course, it's actually a lot more complicated than that. So Les, why is it so difficult, or what are the big challenges in designing a very efficient AI chip?
Right. This is not the first time I've heard that comment. So there's a couple of things. First is that matrix multiply is a very important, but not the only operation that's needed to really run neural networks, particularly a wide range of neural networks that you use in automotive applications. But the other big problem is that keeping a large matrix multiply unit busy is a big challenge. So the bottleneck that you run into, the most important bottleneck is actually getting data from DRAM into the matrix multiply unit at a rate that can sustain its, a good percentage of its compute capability. And in a typical chip, this really limits the efficiency. A typical GPU might be less than 10% efficient in a lot of networks. So we spend a lot of energy to try to optimize that efficiency as much as possible with various techniques. And right now we're about 1/10 of the DRAM bandwidth to process the same network as a typical GPU.
Bob, what do you see as the business opportunity for chips in AI and then AI in automotive?
Well, I think the biggest was the bet that we made on Mobileye and the ingredients inside to enable ADAS and autonomous driving. So, that for us was a $15 billion bet 5 years ago, and I should have said that Mobileye today is worth 35 billion or something in that magnitude. So, autonomous driving, but it's just going to be. I'm a strong believer that AI in general, generative AI specifically, is going to dramatically change every industry. And I know the automotive industry, as an adopter of technology, is going to take AI and make it incredibly relevant, not just in the design of the cars, but in the design of the supply chain and the design of serviceability of those cars, with more predictive maintenance, with the infotainment. The car is going to be a computer and it's going to be joyful, and the infotainment and the chips required, I think, becomes increasingly important, and robotics. So in so many ways, I think the industry has adopted AI as a massive enabler, both in terms of the product feature set, but also in terms of how the shop or inside the four walls works. And I think that's only going to accelerate going forward.
So we can't talk about chips without talking about safety in automotive, of course. And software guys, we typically just think about safety in the context of software and having good algorithms. But there's actually, of course, a hardware layer here as well. So Les, what does safety entail at the semiconductor level? Is it all about redundant compute, or is there more to it?
Yeah, so safety is it's a very complicated topic and sometimes controversial topic. But at the hardware level, it's really driven by what's going on at the system, what the system requirements are. And in the last session you heard there's kind of a wide range of autonomy systems from L2, L3, L4, and ultimately L5, and the requirements are quite different. So at one extreme, we have customers who will take one of our standard chips with auto-qual certification, but it's basically a standard chip, and couple that with a separate microcontroller, an ASIL-D microcontroller. And by doing that, they can reach an acceptable level of safety for a basic L2 system, because the driver is responsible ultimately for the car, and as long as the system doesn't do anything crazy like, you know, steer off the road suddenly, you're okay. But in an L4 type of system, of course, it's much more stringent, and typically what you'll see there is, first of all, you may have dual processing paths, a primary driving path and a fallback path, and the hardware will switch from the primary path to the fallback path if there's some error that's detected in the primary path. And then inside each of those paths, you need to have ASIL-D reliability of the hardware, which means you need essentially multiple chips to cross-check each other and implement that error checking requirement.
And these advanced technologies, of course, are great as long as there's demand for them, but demand has a lot to do with costs. So Bob, how did Intel think about the costs of chips, considering chip performance and the trade-offs between cost and demand?
Yeah, well, there's a concept that I'm sure you're all familiar with called Moore's Law, and you know the simplicity of Moore's Law is that you can double the number of transistors on an integrated circuit every 2 years. So whether the double or every 2 years continues to play out, this concept will continue to live on, in my view. The implications of that are you have more power and or in a smaller package and or lower cost and or more features. So that's the opportunity you have with that space and the additional transistors. And then along the way, with Intel in the industry, and particularly it started with the PC industry and evolved to the server industry, but it was how do you take that incremental performance at lower cost with the possibility of more features and engage with the OEMs about what kind of trade-offs do we want to make. We can take X% cost out and share that with you, or we can leverage the additional transistors in that same package, that same size, to drive more feature functionality. And that's an ongoing dialogue with every new step in the Moore's Law curve. Over the years, there was always a lower price with each new node. There was a give back. And the belief in the industry was that trade-off will drive more and more applications for a bigger and bigger TAM for the OEMs and for, in this case, Intel, to share in a much bigger market over time. And I think that equation has stood the test of time. And I'm sure that equation will work as well in the automotive industry, where, you know, even 5 years ago, when we looked at the Mobileye technology for autonomous driving, it was, for all intents and purposes, required a server in a trunk. So obviously, there's only going to be a handful of cars that drive around with a server in a trunk. But wind the clock forward, and it's just going to be, you know, several cameras, relatively small cameras that nobody will see. So I think that will play out over time, where early on, the luxury higher price product, in this case cars, will have compute. But over time, all automobiles will have the power in a very small package of what chip technology can do for the auto industry.
Les, of course, Ambarella is relatively new in the auto industry and is getting really deep now with a number of automakers. What are you seeing with regards to the appetite to effectively pay for the most advanced technologies?
Right. So I think you see a different appetite from the R&D team versus the purchasing department. And that is a kind of big challenge. So of course, we have to provide a range of solutions that cover everything from a basic L2 system all the way up to L4 as part of that. But I think the key really is that you need to have a close partnership with both the Tier 1 and the OEM on the requirements of the system, because it's very easy for an R&D team to create a bunch of requirements in a vacuum. But when you actually look at what is the cost trade-off between different requirements and chip cost, it requires a very deep discussion to develop the optimal solution for that.
And related to this as well, Les, how do you think about differentiation for Ambarella?
Yeah, so I think our strategy is based on kind of 4 pillars. The first one is that we believe that AI is the future, particularly as you try to go up the autonomy levels for L3, L4. And that means AI on all levels of the stack. And to do that, you need the most efficient AI processing possible. And we think we have the best solution for that. Another key parameter, as we were just discussing, is having a range of solutions that can cover with a single software compatible family, so you don't need to develop all your software from scratch at each level. And then be able to provide a mature set of tools that allow customers to port their software as needed. So we have an open software, and we can provide modules from our stack, or customer can develop everything from scratch, or we can provide potentially an even bigger piece of the stack.
So lastly, I want to talk about the concept of upgradability in vehicles. So people commonly replace their phones every 2 years, maybe 3 years, but vehicles are designed to last at least 12 years. That's several generations of advancements in semiconductors. And of course, vehicle software is improving pretty quickly, and there's consumer demand for better experiences. So Bob, how do you think that OEM should be thinking about obsolescence of chip technology in vehicles? And do you think there's actually a business opportunity for chip upgrades in vehicles?
Well, I think that a 12-year life with a 2-year innovation cycle has to be bridged, and in many ways. And again, the PC, the phone, mobile phone industry have kind of been through this. And the bridging, do you want to reduce the life? Design an automobile not for 12 years, but for 10, but for 8. And how do you upgrade? Upgradability of your designs. How much more important is that now than it was in the past? And my belief is somewhere a combination of both. And upgradability, and the industry has been phenomenal about design for cost, design for maintainability. So I do think design for upgradability, as long as you have that big a gap on the rate of innovation for an increasing componentry of the automobile, that gap has got to be closed. And I think design for upgradability, whether it's software, probably on a more frequent basis, but hardware probably has to happen, more often going forward than it has in the past. And again, the industry has figured out how to design for blank over time. I think design for upgradability is going to be an important consideration.
And Les, what do you think about this from the technical feasibility standpoint, actually upgrading compute in vehicles?
Well, I think it's definitely possible because Tesla has already done it once, right? So making the central server module upgradable is definitely feasible. It's a bigger challenge on the sensor suite because you have sensors mounted all over the car with wiring embedded in the car. So I think it's important to try to get the right sensor suite up front that can be scaled into the future. And then even in the central server, it's desirable to be able to have some headroom so that you can provide software upgrades without having to replace the hardware.
With that, we're at time. Thank you so much, Bob and Les.
Thank you.